now moderating this session. So this is the session on the first session on invited projects, and these are the projects from the first call on 5G for CAM, the first projects I mentioned. The sequence is as follows. First, we will present the project 5G Carmen, then the project 5G Croco, and then the project 5G Mobix. The last one has two different corridors, so they will be presented in sequence as indicated. So let me now move, hoping that Matteo and Andreas would be already there. So I will introduce briefly the two speakers. Matteo is project coordinator, Andreas is the technical manager of the project. Matteo is head of project management group and digital transformation program manager at FPK. As I said, he's the project coordinator of 5G Carmen, also another project Interlink. He received his PhD in computer science from the University of Trento in 2006. He works as a postdoctoral research assistant at the University of Southern California, where I came from as well, so interesting. And he has been working a number of projects, EU projects and also Italian projects. Andreas is from T-Systems International, has a leading role in Deutsche Telekom 5G program with a focus on traffic, infrastructure, mobility, and autonomous driving. He has a number of patents in this area, and he works in the inter-MNO collaboration improvements in accordance with 5G PPP and the EU. So I give you now the floor to Matteo and Andrea.
Thank you. Okay, perfect. So welcome everyone. As Jorge said, I'm Matteo Gerosa. I'm the head of PMO of Fondazione Bruno Kessler, and I will present an overview of project 5G Carmen, that is 5G for connected and automated road mobility in the European Union, together with the technical manager of the project, Andreas Heider-Aviet from Deutsche Telekom. So this is the outline of the presentation. I will mainly talk about the project overview and the use cases and trials, while the more technical aspect will be covered by Andreas, so field measurement, 5G network assessment, and the 5G Carmen solution. So what is 5G Carmen? Is a corridor project over the Bologna-Munich corridor. Is 600 kilometers across 3 countries, Italy, Austria, and Germany, interconnecting 2 major industrial poles. The goal is elaborating and evaluating the benefit of 5G and related service for automated driving in real-world conditions, and ensuring service continuity in different cross-border scenarios, enabling connected collaborative automated mobility and automation level 4. So the goal is to assess the essential 5G KPIs for vehicle and MAC-based service to pave the road for European mobility. So within our project, we have most of the major stakeholders of this environment. We have car manufacturers, we have network operators, we have also road authority, we have the Brenner Road, and of course, research center and a university that works in this field. What are the trials? The goal is to demonstrate level 4 automated driving through 2 key use cases for connected and collaborative automated driving. As I said, targeting level 4 automation, thanks to improved awareness of the surrounding, integrated edge service, and dynamic end-to-end service orchestration. And there are 2, let's say, main key use cases that they are like overarching use cases that then are divided in smaller cases. One is cooperative and automated lane change maneuvers. And here we are working on a centralized approach, match service based, showing low latency vehicle to network communication through a decentralized approach based on the V2M2V communication and an edge orchestrated emergency vehicle clearance. And then we are also, the second use case, overarching use case, is about cooperative and automated in-lane maneuvers. And here we have a situation-dependent mech vehicle local dynamic max synchronization, for example, for cruise control, but this is just an example of these trials. Let me go into more details. So here, let's suppose that a vehicle needs to change lane from overtaking to first lane or vice versa. And the vehicle, you see this vehicle performs lateral control in level 4 thanks to a very accurate and timely awareness of the surrounding enabled by 5G. So here, the use case include, for example, two sub-use cases: the cooperative lane merge in a new lane as originally planned by the vehicle. So see here, let me show you. So here, the vehicle needs, in this represent the second case, the vehicle need clearance for an emergency in the vehicle that's no far advanced through MEC. So we are the vehicle here and the lane change, and then lane keeping while emergency vehicle passes. In the second case, a similar case, there is an initial intention to overtake from this vehicle, but and there is a vehicle non-equipped far behind that moves at very high speed, and the next lane change in this case fall outside the automation, and so the decision is to keep the lane keeping. Another case is the cooperative and automated in-lane maneuvers. This is a case where a vehicle is on the first lane and plans to exit the motorway in moderate high traffic situation, with vehicles in front obstructing the view, so the driver cannot see it. And a queue or obstacle on the exit lane would require the driver to take over, but thanks to 5G, however, the vehicle can sense what the vehicle in front senses, and thus decides to keep L4 and stay in lane, replanning the exit without disturbing the driver. So here, for example, this is the situation. Basically, the overarching goal of this use case is to treat scenarios where there is a change from automation from L4 to the driver that takes control. What are the situations? Of course, we had delays in field test and also 5G rollout due to COVID-19. Basically, especially for a cross-border project, we have some issue like the Austrian border that is closed, site access for Mac installation. But now we are doing ongoing integration and functionality performance test for 5G ID enabler like V2X, Mac service, ANQP broker, GeoService, and so on. This is going on right now, and we are performing near the border test in June, July. And it is planned that we will restart cross-border trials in Q3 2021, starting from September. This is, and now I leave the floor to Andreas. Andreas, would you like to present, or should I just go down and you tell me go down?
Yeah, maybe it's easier you keep it so
okay.
We can move on faster. Yeah. So hello everyone, also from my side. You just saw the use cases, which maybe seem a bit easy, but behind it there's a complex architecture, and I try to show you on this picture the overall setup. Yeah, you have the use cases with various supporting services on the edge servers, and these services are mainly, of course, the maneuvering service, but also a dedicated service for the back situation awareness use case and a local dynamic map and other supporting services. All these services are, of course, communicating with various messages, message formats, and information via the network, via the message brokers, sorry, and of course also the vehicles directly between each other using PC5 communication. And this communication setup is actually a harmonized architecture across all countries, as you can see on the left side. So meaning we have the same setup at all three borders with these services, and also integrated into an end-to-end orchestration platform which is not the detail for today, but other sessions will talk more about this. And this is basically our end-to-end setup, which allows demonstrations of these use cases in the next month, depending on Corona and other factors. Next slide, please. So one thing we did in the field was the assessment of the current cross-border situation, which is probably the same all around Europe. We're having a mixture of 4G and 5G deployments. As said in 5G Carmen, it's coming very soon, the 5G radio. But in any case, the cross-border inter-payment handover is not available in the live networks. Maybe also to mention, Carmen is all about live networks. So what happens is we have the network reselection. And as you can see in the picture, as long as the home network is still available, the automated vehicle tries to stick to the home network. And this goes even down to lower bands. You can see in the lower picture, it even stays then connected to 2G. And only if the home network is not available anymore at all, then it applies a frequency search and tries to reattach to a visited PLN. And this situation leads to a connectivity gap depending on many factors like topology, like the network setups, like net steering of roaming and other configurations. But in general, it's between 10 and 100 seconds. And we have to improve this situation. Oh, next slide, please. So since the live tests and demonstrations were a bit limited, our focus, or we did a lot of work in the laboratory environments. However, I mean, this gives crucial insights into the different technology and setup. We had real traffic data from the road operators, and we are modeling, for example, the area of the Brennero Pass, the Italian-Austrian border, to see the best setup and the best topologies and integration for the various technologies. We're testing new radio and LTE, also combinations of each, and of course with the PC5 mode 4 for the direct communication. So with these different settings and KPIs, we could measure the impact to the maneuvering use case. For example, with delayed messages, how's the success rate of a maneuvering ongoing, and yeah, what's the impact for the vehicles? For example, in worst case, they have to be on their own and switch to a direct mode. But this is, again, very complex, and you have to read our papers and deliverables for more details. Also, we have to mention we have the same radio resources, and there might be different slices and different services requesting these kind of resources. So this kind of coexistence leads to complicated situations, and we prepare this in the laboratory environments to assess the different conditions and consequences. And nonetheless, it's also a question about scalability. We have the real road data and the road traffic and so on, and also equipped and non-equipped vehicles. And our laboratory assessment gives insights on how this will scale in the next years. Next slide, please. We assessed, however, the real situation only also. And you all might know we have the 5G architecture, which also states that we need the XN interface between the RAN. But cross-border, it's very difficult to implement, not only a question of costs, but also really technically and operationally, even if it's tunneled via the IPX networks. And what we also assessed it, even with this interface, we don't have enough data from the foreign MNOs to really manage the handover and everything related. That's the point of the network management systems, the OSS systems, which are historically, of course, operated by each MNO for national operations. And you have also taken into account that it's not just 5G. We will probably not have a pure 5G network soon anywhere. These OSS systems have to manage several generations in parallel, and of course also different technologies and implementations of these technologies. That is very complicated. So as stated here, you see there's a more or less missing interface between the different OSS systems, which is needed to exchange data to have really the seamless handover in any condition. I get back to this later, but first I will also explain about the IPX networks, which are essential. Next slide, please. So the IPX networks are the networks between the operators, and it's mostly not a direct connection, but as you can see in the picture, you have several IPX operators in between. And then there are interconnection points. The peering points are in Amsterdam, in Stockholm, in Frankfurt, or other points, depending on the IPX provider. And these topics are also progressing, however, also takes time. For example, for the trust between the MNOs and this IPX provider, that's actually the ones who implement the N32 interface via the secure edge proxy. So there are discussions about certificates, security, and so on at the GSMA working groups. And very closely linked to this topic are also the end-to-end SLAs. So until recently, there were no end-to-end SLAs, only between, for example, operators and one IPX provider, or between two different IPX providers, but no end-to-end SLAs. This is now standardized, but it will take time until this is implemented everywhere on every IPX provider and every MNO. And here also, there's a latency question. We have measurements from our colleagues from Global Carrier, which is an IPX operator from Deutsche Telekom, and the latency as such is quite good. But this is also depending, again, on each IPX provider and MNO and what route is used. So long story short, there are improvements ongoing. And here we also could have the same discussion as for the MAC. If you want to have really low latency, some milliseconds, it's a question of costs. Yeah? Costs and needs, same as the MAC. So next slide, please. So to finish, I will come back to our real scenario. The thing is, in Europe, you will most likely not have the same technology, the same access technology everywhere. Yeah, you have my 4G, 5G, 3G, 5G, or any other combination. So it's unlikely that we have the seamless handover anytime soon everywhere. Yeah, there's always often interrupt, which is complicated. In 5G Carmen, we therefore opted for the accelerated reselection. This is in fact complementary to Crocro Mobix, which really do the handover. We have this more pragmatic approach. In our laboratory, this already led to less than a second network interruption at the border. And by simply technologies like equivalent PLM, so this means the UE doesn't stick to the home network. We establish cell neighbor relations with the domestic and foreign cells. And by cell redirection procedures, we can indicate the preferred foreign cells so that the UE doesn't have to scan the whole spectrum for potential PLMs and cells. And additionally, to have this RAN data I mentioned before, this OSS data, we concepted a shared distributed database for this kind of RAN data sharing, which is configuration data like cell PCIs and so on, but it's not much data. But this needs to be shared among MNOs for the border sections in order to have the fast reselection and or the handover. And for this kind of network governance, I would call it data sharing, we started an activity in the GSMA because there are more operators than just in Carmen or other projects, because this has to be a kind of non-discriminatory border area database for having this data and using it in the OSS and in the RAN. And to finish it, there's also the DigiConnect colleague who made a good statement last week at the 6th Symposium. So we don't have to talk about the digital interface, but Europe must work together on this. And with this, I'd like to finish our part.
Thank you. It was very quick indeed. I don't see many questions in the question and answer session here, but I have a few, if you don't mind, that have to do exactly to this mix of technologies, even 2G, but 3G, 4G, and 5G, and the need for seamless handover between technologies, even at the border. So how will this be implemented if there are a number of interfaces that are missing, as you have shown there? Also, even at national level, in countries especially that require national roaming or call for national roaming, how do you address this in terms of inter-OSS agreements and interfaces? Andreas,
I'm not sure I understood the question. So for the real OSS interfaces, it's more work to do. To integrate it in each MNO legacy infrastructure. What we propose is set a shared database which has this RAN data, and of course also secure, because this is sensible data for each MNO. And we still have to define the interface, of course, between the OSS systems and this shared database. But this should be a more joint work, and probably also beyond 5G Carmen.
But how are you going to manage this 3G, 4G, 5G interaction in real terms? As you move across the border, consider as well the use of the 700 megahertz bands. How are you going to be able to manage all of this in order to provide this seamless service?
So for the interfaces, it's complicated, and probably cannot do it in 5G Carmen. But once you have the RAN data from the foreign MNOs, you can configure it in the own OSS systems, which is then used for standard procedures, which also apply at least starting from 4G. So we can show this in 4G and 5G, and in the future it will also work for 6G, I guess. Or maybe I didn't understand your question then.
One question is about vehicle-to-vehicle communication via PC5. How do we execute that? Do you already use the dedicated chipsets from Qualcomm, or are you using open source / SDR based implementations?
We're using the Qualcomm chipset, which provide, I think it was released 14 V2X based, the one named in one of the presentations this morning. But for details, I would also have to refer to Qualcomm, who's hopefully on the line.
Yeah, I think he already, Ricardo already left.
Yeah.
Okay, I don't see any more questions here, but concretely in terms of the cross-border segments, so what do you expect to be able to show by the end of the year in terms of actual cross-border use cases? Or if not this year, what is the plan in terms of showcasing true cross-border use cases?
Well, given that COVID lets us pass the border, we will show our use cases already cross-border. Depending on the implementation on the network side, for the vehicles, they might switch back to the direct communication mode. This is actually the default, or I won't say fallback, but always possible. It depends also on the network quality. We are also having a QoS activity, which can predict, okay, network will be good or not good enough. So the vehicles dynamically switch between the network supported communication maneuvering or vehicle-to-vehicle maneuvering. And best case, but still, is we have the fast reselection implemented, and then we can already show it end of this year.
Yeah. Just to be concrete, how many vehicles are you really using in these tests?
We have 3 vehicles for the different. Sorry?
No, please go on. I was intrigued to
what 3 vehicles are the minimum for the maneuvers, plus the emergency vehicle, of course, for this special use case.
Okay, very good. Okay, since there are no further questions, I thank you again. Again, this is a presentation from Project 5G Carmen, the German, Austrian, Italian cross-border corridor project. The next presentation is from Project 5G Kroku. The presenter is Dr. Dirk Hetzer, a senior expert at T-Systems International since 2014. As I said, he's the technical project manager of 5G Kroku. He studied the electrical engineering at Humboldt University in Berlin, and obtained his PhD in informatics from Potsdam University in 2004. So I give the floor to Dirk, please.
Okay, so 5G cross-border control, one of the sister projects together with Carmen and Mobix. We had this nice introduction this morning already from George to give the global picture for this activity. And I will go to present here in my talk a little bit about the project itself, and then I will go in very few details for the dedicated use cases. Of course, we have already worked 2.5 years, and we have nearly 100 public slides prepared for such a presentation, and it's quite clear that I cannot really go for all. But please go then and on our webpage. You will find all these details, all this background information in our deliverables. And it's, of course, not possible to present here in this talk all these parts. Overview for the 5G COCO is that we have 3 use cases selected for the presentation in a cross-border scenario. This is teleoperated driving, high D map generation and distributing of this map for autonomous driving, and anticipated cooperative collision avoidance. And these 3 use cases are to present in this already mentioned cross-border scenario. And we have heard that the motivation is coming from the current situation that in cross-border constellations, you will find more than 10, sometimes 30, 50, 100 seconds delay or outage of the network. And this is, of course, not a good basis for this use cases in a European context. The project itself is related or connected with very strong partners from these different countries. We have 24 partners with coordination from CTTC in Spain. And to go a little more in details, we have the telco equipment partners, we have the mobile network operator, we have road traffic authorities, we have OEMs, tier ones, and of course SME academia, combined with an explicit support from our governments. Demonstration piloting itself is planned to be done in the area of Schengen on the border between France, Germany, and Luxembourg. The technical focus is, of course, already mentioned, this cross-border aspect. We will use 5G Neo Radio. We will go for dedicated quality of service usage with QoS prediction. We will use mobile edge computing, especially to overcome this reconnection of the network to have this fast track. And we will go, of course, for operational issues for management and orchestration for software-defined networks between different MNOs. And now, last but not least, we will also use, already mentioned this morning, precise positioning for these automotive use cases. There are 2 big corridors. One is here shown on the left side, is a German-Luxembourg corridor, the other one France-German corridor. They are in preparation, so our first big test is done this summer in July. Yeah, we have the same issues with the COVID constellation, and the second test round will be done in September. And to prepare this test, we already used all the building blocks in our so-called small test site deployments and scenarios, so that we already presented and tested all these parts of our use cases in Barcelona and Astra Zero, on the A9 in Germany, in Munich, and Monterrey in France. To go a little more in the details of our use case, we have this teleoperated driving as a very important building block for the highly automated driving, especially, of course, mainly in the direction for an fallback constellation if the autonomous driving function needs to be supported by a remote driver. In principle, we have here 2 main parts. This is one, this so-called direct driving mode, and the other one is the indirect driving mode. And in this picture, you see that this driving is possible then with a direct driver, and we have made this tests with the colleagues from Bosch and TU Munich, that here in our results, in brackets still using 4G, we can show that the steering and the speeding up and braking is working properly. We have more or less system work as designed, that our let's say needed relations is more or less cutting or complete in the same line like we have to do it in for this driving. And on the lower part, you also see our measurements for the class-to-class latencies. Of course, this is still here quite high for the 4G usage, and I will show later on a few 5G pictures so that we can really see that we will be able to improve this. Especially for the teleoperated driving, we need the quality in the network, and also a very demanding uplink request. And for this, we have implemented this so-called prediction of quality of service and as a special client in the box, and combined with a predictive QoS server to give a driver, let's say the stability that he will never be lost in the way where he has planned to go according this prediction for the network quality. And I think this is a function not only helpfully in the future for automotive, this will also have many other, let's say, use cases to use this network prediction in the future. Second big use case is high definition maps generation distribution for autonomous driving. And here is such a scenario. You will have a car detecting some changes, whatever accidents on the street, and sending this back to a backend and to be redistributed then to another country, to another over another MNO to the following cars, so that we can really show here that we are able to close the loop. Here is an example. We have an sign 110 in the map. The car itself detects that there is a new sign with 90, and then the speed limit is adapted to the map for the next car, so that this information is updated, and we can show that this loop is closed in our pilot and trial environment. Here you see very interesting figures for the constellation that we have 5G mobile edge computing, and in the combination with 5G standard public internet and 4G and 4G public internet. And you see that especially the difference, of course, between 4G and 5G is quite high. And also the gain of the mobile edge for our use case is significant to give a very strong motivation why this solution combined with 5G MEC and 5G at all is a very strong building block for such a use case. Our last use case is anticipated cooperative collision control. It's let's say not so far away from this what we have learned in the presentation from Carmen. We have here a use case where we have a collaboration between different car makers to show how they can interact between each other with help of mobile edge and with an according backend. Here you have our user story, one of the user stories to show how this is working from one side of the border. There is a problem. to be transferred to the car from the other side, and of course not only to a car from one fleet, also to a car in mixed fleet with different OEMs. And here you see, especially for this first test we had made, also the very strong influence of the mobile edge deployment. This is a gain for more than 30 milliseconds, and it's quite dramatically good that we can show these results also between different operators. That means between different borders here in our pilot environment. One other aspect of our work was to go for this business potentials and cost-benefit analytics in these use cases, but of course not only for these use cases. And so we made deep look inside who has to work together, how we will use different sources to go for this business case evaluations, of course in relation with our sister projects and with other relevant organizations. Name it 5GA, we had already from Monk this morning, 3GPP of course, EATA, and so on, ETSI of course. And we have found that there are many new stakeholders in a link, and we have then, especially for our use cases, made an evaluation where we have to play together in the future. And here are a few examples how complex such an, let's say in brackets, simple use case has to be deployed in the future with many players going from MEC providers over teleoperator provider to map provider, car OEMs, of course, OEMs, telco spectrum regulation, mobility service provider, and so on. And all they have to work together to find a winning constellation for these different new partners. And of course, for the other use cases, it's quite in the same area that we have really to play with this new relations and constellations, and already discussed in the other talk that we need at the end real new discussions, for instance, in the roaming between mobile network operator to have an, let's say, call it quality roaming with quality of service between different operators. But it's not only one of the points. We have many other new relations, and of course new value changes for these use cases. To end up in our pilot environments, we have shown that we can work over cross-border scenarios with the requested end-to-end latency requirements. We are able to support with help of 5G and MEC the very short handover scenario. The idea behind is make before break. That means we have a connection to the new MAC before we will lose the connection to the old MAC. And the trials are showing that we can demonstrate these use cases between different operators and countries. Thank you for your attention, and of course I'm open for questions.
Thanks, Dirk, for this presentation. Questions from the audience? Okay. What are the main challenges faced regarding TOD interface UC1?
Yeah, for the TOD is of course for the network itself. We have an extreme high uplink bandwidth need. That means we have to transfer something like 5 video streams with high quality that will end up with more than 20-30 megabit. And the second part is that we have different regulations, so that in some areas it may happen that it's not allowed for legal reasons to use the so-called direct driving mode, and we have to use an indirect driving mode. It means that the operator will only decide a proposed trajectory to go. Yeah.
If I may, in your presentation, you mentioned that the delays, the latencies are acceptable. How acceptable are they? If you are talking about real-time services, and especially continuity of real-time services across borders, how far are we from this? Okay, will this only be achieved with 5G new radio? What is the status from your perspective?
Yeah, to take the example for the TOD, yeah, if you will come down to about 150 milliseconds, this is quite sufficient for this use case, and this is possible with this MEC fast handover, and you do not necessarily need the 5G. You can do it also the 5G new radio. You can also do it in a 5G NSA environment. Yeah.
Mm-hmm. So in terms of time plan for the availability of these use cases, what is your perspective? If it's not dependent on 5G new radio, when do you think that you will be able to convince the automotive sector to deploy these services or to use these services?
Yeah, that's of course a little tricky to know what the market is demanding. For us as telco operator, we will be ready about 23 with the network in these relations, but I cannot make any promise how fast then the automotive partner are really willing to deploy such services, especially in the high-end cars, like take an Audi A8 and BMW M5 X5. The parts are already in the car, yeah. So that especially for the highway assistant solution, there is already more or less all parts already prepared, and we have really to put this in combination then with the authority, with the legal constraints. Yeah.
Mm-hmm. Okay, good. I see no more questions. Okay. Maybe one that has to do with the vehicles. Again, the same question. What vehicles are you using for these trials?
Yeah, we have together with Bosch, Volkswagen, Renault, and Peugeot. And in the numbers you asked also, Carmen, I'm not 100% sure. At the end, I think it's 4.
Okay. Yep.
But from different partners then, yeah.
Okay, that is an important aspect. Since you have 3 countries involved, are you able really to make sure that there is the interfaces are working not only in terms of MACs but also in terms of operators from different groups? Okay, that it's not as in the case of Carmen, the Deutsche Telekom group. So can you really interact among Mac providers? Can you interact among different operator groups and equipment providers? So can you really have a mix of operators, Ericsson, Nokia, or have you tested this variety, and have you tested end-to-end interoperability within the required latencies for this diversity?
Yeah, we have not tested all the combinations. And one important reason is that we have in our trials, we are not connected to the real 5G network. We have our pilot 5G networks in the different places. So and the reason behind is that the real network is not deployed in these areas. So for this reason, we have not really used, like the common guys, the standard public network, and so we have more flexibility to adapt the solution. And we have made some cross-functional tests, of course, between different networks, different car manufacturers, but we have not put all these different possible solutions together, not yet.
Yep. A final question that's also is common to Carmen is what is the use that you are considering for the 700 megahertz band to provide this umbrella coverage of different areas?
Yeah, it's a little bit. Let's say it's not of. I cannot make any official statement. I can only make. Tell you something about my personal opinion for this. Yeah, it's not a Deutsche Telekom opinion, and of course the 700 megahertz is a very very good building block for rural areas, and this will of course be in combination with an LTE deployment. So if you have a very good LTE coverage, then the additional value of this 700 band is not so high, but of course it's very high for the areas where you have an bad LTE coverage, and so you will have this mixture in different scenarios, I believe. Yeah.
Okay. Very good, Dirk. Thank you so very much. There was just a question on a variety of MEC providers. What MEC providers have you considered thus far?
We have as Deutsche Telekom, we have an own MEC service, and we have used for the project this together with the colleagues from Huawei and Ericsson.
Okay, very good. So once again, thank you so much, Dirk. Thanks for your presentation. So this was a presentation again from the project 5G Croco that addresses the triangle France, Luxembourg, Germany. Thank you so much.
Yeah, okay.
Okay. So we now go to the next presentation. So yes, so the next presentation is from the project 5G Mobix. There will be three presenters. Koen Bresser is the project coordinator from Ertico, and then we will have presentations from the two cross-border corridors, the Spanish-Portuguese corridor and the Greek-Turk corridor. Okay, so I will introduce them very briefly. If it works, Koen Bresser joined Ertico's innovation and deployment team in July 2020, and his expertise relies on 5G connectivity and automation. He worked before in Sweco and TNO, so he has a lot of experience in this area. He has been responsible for 5G Mobix, and his work extends into transportation projects involving port implementation solutions based on 5G. He holds a Master of Science in Electronic Engineering from the University of Twente in the Netherlands. So please, Koen will introduce, as I said, the project overall. Thank you, Koen.
Thanks for your introduction, George. Let's see which screen will be shown. This one. Okay. As George mentioned, 5G Mobix is a project that contains two cross-border corridors, so it's best to start with an overview from a high level. And actually, I want to start with where does the project come from before we continue with where do we go. It's part of their four main goals in Horizon 2020. This one is the specific one, is the societal challenges. And the subtopic is smart, green, and integrated transport, from which ICT 18 came forward. This is also for the other two projects as well. ICT 18 can be summarized very quickly as 5G for CAM. The intention is to qualify 5G as a core connectivity, to demonstrate the benefits and support the strategic objective to have all the major transport paths covered by 5G in 2035, which automatically introduces the cross-border aspect. So how do we address that? The numbers, it's running from 2018, November to July 2022, and we have around 50 partners from 11 countries in Europe, with an additional 10 in non-EU funded partners from China and South Korea. So it's a very broad group of partners. And the objective is to accelerate the deployments. To do that, we carry out trials. In these trials, we want to qualify the infrastructure, not only on technology or what we should do with spectrum, but also a business part of it. Because if there's no business case or if there's no way to cooperate, then this will not happen. So that means cost-benefit analysis, business opportunities, and legal and regulatory security issues are a very relevant part as well. The project, the trials, as mentioned, we have a set of countries, set of partners from 11 countries. That means that we have two cross-border corridors, one in Spain, Portugal, the other in Greece, Turkey, which is a very interesting one because it crosses a legal boundary as well. We go from the EU law towards Turkish law. And the corridors are complemented by 6 European and Asian trials. With these trials, we can have a broader view on what can be done, then we can achieve only with cross-border trials. The network itself is composed of a little less than 30 5G GNODs. And initially it is an NSA architecture, but we also try to go towards SA, and we have quite some use cases in which that is being performed at the moment, so that's good. To answer your question on vehicles, yours, it's already there. We have 20 SA level 4 automated vehicles, and the use cases themselves, we have around 25 use cases, which are grouped in 5 categories that you see below. So it's advanced driving, vehicles platooning, extended sensors, remote driving, and vehicle quality of service support. To be able to combine the results into learnings, we need to have a clear understanding on how we approach this. This picture is incorrect. This is part of the proposal, but if you would draw the correct picture, it wouldn't fit on a single page. So this is just for explanation of the basic concept, which has evolved, of course. What you see is basically we use 2 slices, one EMBB for large amounts of data and one URLLC slice for the low latencies. And using these slices and interconnections between the operators, we want to ensure that we can cover all the use cases and all the necessary functionalities. Well, if we have the data, we analyze it so that we have business models, stakeholders and the relationships, sustainability targets, and deployment strategies. To give you some insights in what we do where, these are the countries in which some of the items that stand out are mentioned. So what you see is we do a new radio millimeter wave in China and Korea. Edge computing is all over. We do some NSA, possible SA, localization, multi-SIM modems. So it's a quite broad amount of use cases and quite broad amount of 5G features that we want to trial. To give you an insight on what we trial, when and where. This picture shows what features are being tested at what site, when. And there's also a similar picture of this for the use cases. That's a little bit more detailed because the features are trialed practically everywhere. So this shows that we will get quite a comprehensive and complete overview of the 5G features that will be relevant to address the cross-border challenges. That we will have them available. Trials have already started, the early trials, and early trials are to assess that everything works correctly and that we get preliminary data, maybe some changes to run the full trials to get the full set of data that we need for evaluation. As mentioned, there's a lot of partners doing this. This is a short overview. There should be some names that you know. And that's basically the introduction from my side. The rest of the presentations will be done by Diana Blanco from Outsource. She will introduce them, I believe. So if you want to, you can take over the screen again and introduce Diana and Natalie. Or if there are questions, this is the brief overview. George, are you there?
Yes, sorry, I was muted. Now we don't have any questions at the moment, but let me go, if I can, directly to my screen. I will introduce now Diana Blanco from CTAG. She is going to present the Portuguese-Spanish cross-border corridor. Just a second. Diana is an industrial engineer specialized in industrial organizations with a diploma of advanced studies, a master's in energy and sustainability, and specialist in logistics and production management. She has more than 10 years of experience as senior analyst and project manager in the energy efficiency sector. She joined CTAG in 2019, where she is focused on the European project. And again, as I said, she leads the Spanish-Portuguese cross-border corridor within the 5G MOBIX project. So I give the floor to Diana, please.
Introduction. My name is Diana Blanco, and I'm the project manager of this project at CTAG, being CTAG the leader of the Spanish-Portuguese cross-border corridor.
Diana, you have to move closer to the mic because it's a bit fuzzy.
Okay. So I would like to begin by expressing my gratitude. You can see the screen well. Okay. Expressing my gratitude to this opportunity to present our corridor here today. And having said that, I will provide an overview of our Spanish-Portuguese cross-border corridor and all work done by our partners to achieve the objectives of this project. Okay, so the Spanish-Portuguese cross-border corridor connects the two cities between Vigo and Porto through the different roads and highways. Specifically, the cross-border is located in northern Portugal and Spain, and crossing the main river through two international bridges. International trade as well as large passenger commuting flows are of great importance and provide ideal conditions.
Diana, sorry, you are breaking up. So if you can again move closer to the mic.
Yeah, that's what I was commenting that international trade as well as large passenger commuting flows are of great importance and provide ideal conditions for the execution of the trials in 5G MOBIX projects. Our consortium is composed of 23 partners, and it is an extremely strong consortium as it includes the main companies of the sector in different areas that will contribute to the success of the Spanish-Portuguese cross-border corridor. In this way, we count on road operators from both countries and city councils who will advise on the best way to execute the test, with MNOs and telecommunication partners that enable the deployment of the 5G network, OEMs that supply the vehicles, with institutes, technological centers, and universities that will allow to go off the hand of the state-of-the-art of the most advanced technologies, testing and homologation companies that will provide an objective vision for the evaluation of the project, and of course, technological companies that will contribute to the deployment of the different user stories at different points. At this point, I will focus on presenting the different user stories that we are going to test in our cross-border corridor. First of all, we have the lane merge. In this case, main autonomous vehicle. This is the blue one, will be incorporated in a motorway. And in the main lanes, there will be autonomous connected and not connected vehicles traveling through them. The autonomous and connected cars send their position to the corresponding MEC thanks to the installation of the nearby 5G antennas. In the case of the unconnected cars, they will be detected by the radar located for this purpose. The MEC receives then the messages transmitted by the vehicles and the radar and forwards them to the nearby vehicles so that the blue main vehicle receives the information regarding the vehicles that start traveling on the main roads of the motorway and predicts the trajectories of the detected vehicles and calculates the collision risk. If necessary, the speed of the cars is adapted and the incorporation maneuver is allowed. The next one is the overtaking. In this case, the blue main autonomous vehicle is driving along a highway and receives messages from the ITS center. It's the overtaking. Sorry. In this way, in this case, the main blue autonomous center is driving on a right-hand side of a motorway, and in front of it and behind it there are two bulky and unconnected vehicles that significantly reduce the vision of its sensors. Another autonomous vehicle runs in the left lane 100 meters behind the main vehicle and at higher speed. And the MEC receives the messages and forwards them to the nearby vehicle so that the blue vehicle can check the safety of the overtaking maneuver. This is when the overtaking maneuver is performed, or if this is not possible, the maneuver is cancelled by the blue car. Now, yes, the HD map user story. In this user story, the main autonomous vehicle is driving along the highway and receives a message from the ITS center notify that we have a road event on the road. And the overview of this vehicle receives information, compares it with the information on its map, and concludes that its internal map is outdated. So it asks the driver to take the control and start recording what sensors see. When the work event ends, the main vehicle continues its route in an autonomous mode, and the overview sends the data recorded to the ITS center, which processes it and generates a new HD map. In this new map is then sent to the nearby vehicles so that they can autonomously overcome the work event. Just to comment that this user story will be replicated with the bus, with the difference that the bus will not be an autonomous vehicle but a manual one. Okay. Also with the ALSA bus, we have the multimedia service for passengers. The bus passengers have tablets to be able to enjoy the high quality multimedia content thanks to the 5G network. And on the other hand, we also have a 4G camera installed on its windshield that will allow the sending of the front and inside view in real time to the control center. We have also two user stories related with an automated autonomous shuttle. And in this scenario, the autonomous shuttle is performing its route in an autonomous mode along the bridge. And at both ends of the bridge, there are areas without visibility of VRU. So in both cases, anti-collision systems are installed and send the detected information to the MEC through 5G. In addition, some VRU will carry a 5G phone with an app that will send information of their position to the MEC, and then the MEC send the messages to the ITS center and the shuttle 5G view. The shuttle then brakes or stops in case there is a risk of accident. And finally, we have the remote control. In this scenario, the shuttle is performing its route in an autonomous mode until the middle of the bridge, and then it faces an static object that blocks its route. So the shuttle stops in a control manner. After a while, the shuttle notifies the control center about the blockade and asks it to take control. The control center then remotely drives the shuttle until it has overcome the obstacle. And once this is done, the autonomous mode will be reactivated and the shuttle can continue its route autonomously. Well, at this point in the presentation, having seen the different user stories, I would like to show in more detail the specific locations where the test will be carried out. As I mentioned before, our corridor is developed between Vigo and Porto, where the user stories related with the 4G monitoring and the multimedia service for passengers in the bus will take place. At the Portuguese level, the lane merge scenario will be deployed on the A28 located near Porto. At the Spanish level, the user stories will be deployed on the A55 motorway. And finally, at the cross-border level, the scenarios will be deployed in the two international bridges that link to and Valencia. This is the so-called Old Bridge, both in which both autonomous shuttle scenario will be deployed, and finally in the so-called New Bridge to deploy the remaining use cases in relation to the lane merge, overtaking, and to execute these use cases, we will rely on 5G technology, of course. So I will briefly show the characteristics in relation to the 5G network, the infrastructures, and the vehicles that we are going to use for this trial. In relation to the 5G network, it's important to highlight that the Portuguese network is completely dedicated for the project, and the Spanish network is using the 16 commercial network, and some of those nodes are used to provide the anchoring necessary in the 5G architecture. To see this better, the core deployment at a cross-border level presents a substantial challenge when the aim is to achieve seamless communication between the networks of two different countries. In the case of our corridor, the implementation of the 5G core in each country is similar with minor differences. The Spanish core is centrally located in Madrid, which is around 500 kilometers away from the test area. So this large distance results in a high latency. Therefore, it's necessary to deploy an edge site with MEC platform, where the most critical device services can run close to the final user. This edge site is located in Vigo, 20 kilometers away from the border, and it allows to drastically reduce the latency. All the nodes involved in the test have a direct connection to the MEC services through the transport network. And of course, similarly, in Portugal, the 5G core is located in Lisbon, and the MEC is located in Rivadavia in Braga. So both MECs are directly interconnected in Vigo. This slide shows the position of the antennas deployed. There are two in Porrinho and two in A28 for the national trials. And of course, we have a 4 on the cross-border to cover both ends of in the two bridges. Regarding the roaming scenarios, we plan to test the home routing and local breakout options. The home routing is expected to be the best solution for B2X services because the higher impact on the continuity is more critical than the lower impact on latency. In relation to the handover, different possibilities have been considered at each side of the border area. The Spanish network, of course, has some limitations. It is shared with Telefónica commercial network. However, it is possible to adjust some of the threshold parameters involved in the handover process. And on the Portuguese side, for the Portuguese network, more possibilities exist since the network is completely dedicated to the project and more parameters can be adjusted. To conclude this section, I would like to emphasize that our corridor collaborates with all the national trial sites in the project to provide solutions to almost all the cross-border issues described by the project, so that the proposed solutions are going to be able to be tested and analyzed in the trial site. Once we have seen the necessary network deployment, we can remote control infrastructure. And in this sense, infrastructure relies on the different roadside devices, cloud infrastructure elements, and remote control equipment. For example, for the vehicle detection, traffic radars are going to be used to provide connected vehicles with information about other vehicles in the road in the lane merge user story. And of course, 5G as used the connectivity link to other sensors in order to provide them with 5G capabilities. In relation to the anti-collision system, these systems are used to provide the connected vehicles with information about the vulnerable user crossing roads. And also 5G smartphones are going to be used as a tool for VRU to protect themselves by warning near vehicles about the VRU situation. Both the anti-collision system and the smartphone app are going to be tested with autonomous shuttle in the old grid. In this same scenario, a drone will be used for traffic safety evaluation purposes by Siemens. In relation to the remote control or remote driver equipment, we create a vehicle cockpit that is used as a tool for driving vehicles remotely in a specific situation. Since here latency is critical in this use case, these devices are directly connected to the MEC. And finally, the ITS centers are used as an ITS platform in the cloud with different objectives: to monitor connected vehicles, to generate road events, and to notify connected vehicles about them, and finally, to generate updates of the vehicle's HD map. Some applications as MQTT, the remote driving application, and others are developed and integrated into the MEC for complementing all the CAM infrastructure. Regarding the vehicles, we are going to use some autonomous vehicles, as you can see in the slide, and some connected vehicle, and also a commercial connected vehicle. But the more we are going to use autonomous shuttle completely developed by CTAC. In relation to the OBUs, so we can see here 3 OBUs that are provided by different partners, and all of them are equipped with the Quectos 5G chipset. In view of all what I have commented, I would like to focus now on the future evaluation of our corridor, which will be carried out from the technical point of view as well as from the user acceptance point of view. So the main objectives of the technical assessments are, well, the objectives are multiple, but focus mainly on the 5G network by analyzing, for example, the difference between home routing and local breakout, the impact of the speed and roaming and handover, the transition between MECs, the difference between the infrastructure decision and the in-vehicle decision, the interoperability devices, the cloud connect applications, the video streaming, and so on. So to achieve these objectives, in our corridor, a methodology based on the analysis and definition of the architecture was followed to define the different points of observation and control, which would be the user equipment, MEC, the ITL centers, and the web in the case of the multimedia streaming. As a second step, the data flows between the different components of the system were defined for the different use cases. As a third step, with the tools to be used for the logging of the application, radio, and network level were also defined and identified. And finally, the test case were described, identifying the different variables to be modified in the test to be performed. In addition to this, technical evaluation and evaluation from the user acceptance point of view would be also carried out. And the motivation for this type of evaluation is based on the concept that the technology considerations have an effect on how we perceive a technological application. And if a well-designed application will be perceived as useless or difficult to use if the technology behind it doesn't work properly, for example, with intermittent connectivity. Therefore, the objective is based on assessing the influence on the perceived acceptability of the service continuity interaction with users. This is going to be done with trials with users and online surveys. In relation to the trials with users, all participants will be passengers of the vehicles, but to collect additional information, we will also evaluate the suitability of the professional and remote drivers. So the acceptability evaluation will be focused in two contexts. The first context with no connectivity breaks in local trials, sorry, and in the second one on the actual boarding in which network transfer processes will be employed. For this, we will use questionnaire, open answer questions and interviews, focus groups, and of course, this will be done also by observation of driving events and participants' behavior. Regarding the online service, we have prepared scenarios for the different use cases, assuming different levels of connectivity performance with textual descriptions, graphical illustrations, and small applications that you can see in the slide. Each respondent will be presented with one of these scenarios and will be asked to answer a validated observability survey. And with this, we expect to be able to anticipate what to expect in terms of acceptability for different levels of connectivity performance. As preliminary results, in addition to the tests being carried out by the different partners to develop their own equipment and systems, some agnostic tests described in the project have been performed on the Spanish side. So in this way, the tests described by the project were launched to perform diagnostic analysis of the network. Regarding the outreach, it's necessary to comment that it could not be crossed during the test because it was completely closed by COVID-19. So these tests were only performed up to its entrance. At this location, as you can see, we have a downlink throughput around 100 megabits per second. In the case of the reach, an example of the result obtained in terms of downlink throughput is shown with higher result about on average about 180 megabits per second. And just to comment that this test will be repeated, of course, when the Portuguese network is fully deployed between the two countries. In relation to the testing schedule, it is expected to start the early trials at national level for renewal in June and continue with the trials until the end of this year. And finally, to conclude, I would like just to very briefly highlight the following points about our cross-border corridor. The characteristics of the border itself with the few bridges allow us to deploy a wide diversity of scenarios to be deployed in projects by a broadly complementary consortium with a clear involvement of the road authorities of both countries. In addition, it's necessary to highlight the strong relationship within the two adjacent municipalities. And all of this along our corridor, of course, in collaboration with the other European partners, in the preparation of the future of the country through the use of 5G-based technologies. We have the geographical, cultural, and commercial conditions to explore different scenarios, and with the information that we will obtain from the evaluation of this project, we hope the sum of the developments may turn into real applications. So this is all from my side. Thank you for your attention.
Thank you, Diana, for this very, very comprehensive presentation. I have only one question. In one of the slides, you mentioned the ISL QoS. What QoS analysis are you doing at the moment?
Yourself?
Yeah.
From yourself?
Yeah, or what kind of QoS analysis are you doing?
Well, we are doing the QoS analysis with the ALSA bus, which is the one that is going to do the complete route between Vigo and Porto. And what we are going to analyze there is the two user stories with the 4D camera to provide these views to the remote control center, and to establish the multimedia content to all the passengers. That's why these two user stories are related with the QoS.
Mm-hmm. Yeah, but since you are mentioning this bus, this bus will pass through many areas where there is no 5G coverage. So are you going to do also a comparative analysis of the services provided where there is 5G coverage, where there is only 4G or even only 3G coverage? Or are you just going to analyze the 5G coverage areas?
Yeah, in fact, that's our idea. Of course, we are now having 5G coverage in all the route between Vigo and Porto, and our idea is to see how 5G can benefit this video transfer to the user, and see if they experience some connectivity problems in these areas in which we have 5G. And if they have the same problems or not in other related areas. So yeah, exactly. It is our intention to do this analysis.
Okay. Thanks again, Diana. So now we will go back to we will go next to the next presentation, which is on the Greek-Turk corridor. It will be presented by Dr. Nazli Güney. She is principal at the 5G R&D department of Turkcell, the leading mobile network operator in Turkey, and focuses on 5G and beyond wireless communication systems. She received her bachelor's, master's, and PhD degrees in electrical and electronic engineering from Boğaziçi University in Istanbul, and she also has executive MBA from the same university. She's also an assistant professor of computer engineering at Rumeli University in Istanbul. So please, Nazil, looking forward to the Greek-Turk cross-border corridor. Thank you.
Hello. I'll keep the webcam on if you hear me well. If there's a problem with the voice, I can turn it off.
No, it's okay.
For now. Okay. So thank you very much once again, Latif and George, for inviting us to this event. It's been a pleasure listening to all these discussions and all these projects once again. It's been a good overview for all of us. And I'll be talking about the GRTR cross-border corridor here today. And my agenda will be first introducing the trial location and our partners. And then I will continue with user stories, our 5G network, more on 5G network because the summit is on 5G for CAM. And then talk more about what we're really doing in terms of verification and integration and what we will be doing next with the trials. And then this trial location, we already talked about this. This is actually, okay. This is a big corridor starting from Istanbul and going all the way to Thessaloniki, actually. But since we're going to be using 5G, we're going to be working on a certain percentage of it, Istanbul to Thessaloniki. But if we zoom a little further, I mean, this is a big corridor actually. So, I mean, zooming in further to see the cross-border area, because we're more interested in cross-border areas and cross-border regions. And looking into this, we're going to be here at the Uppsala border area. This is the Uppsala border here, and then we have the Kipi border here, and we're going to be extending from here to here with 5G connectivity. So, and this is actually the river is kind of the border around and changing here, and this is the border between Greece and Turkey. So this is actually where we are. And that was a map of a satellite map, but when we look in pictures, we see that it's actually the area can be quite frustrating at times when there are a lot of passengers and trucks, cargo that is being carried in high seasons, or there's a disturbance in the area, because as you see here, down here, we have controls and rigorous controls and checks and a hard border area on both sides, on Uppsala side and on the Greek side, on the Kipi side, there are controls. So, and there's a bridge connecting the two countries. So this is a difficult region. I mean, it's not like the other borders in the EU. So we took special notice of this and designed our user stories, we call them, according to the needs of the specific cross-border area. So looking once again into this area, we see we have 2 border gates that should be crossed, and we will be conducting the trials along this about 10-kilometer road. And for this, we have border crossing permissions, and we need the public authority permissions for using the customs areas. That kind of permissions is required to perform the trials. And the area is, as you saw, it's quite distant from Istanbul, which is a major hub for trade, transport, and logistics. So, and also other areas. So we will first do our development and testing activities in Fort Otosan test site, and this we will use as a local trial site area, test area. For our user story development and development activities, and then move over to the trial cross-border trial site as needed. So I gave a hint about one of the partners of the GRTR corridor, it's Fort Otosan. So let's look at the others. In addition to Fort Otosan, because we're going to be using 5G network, core network, RAN deployment, who's going to be those partners? It's Turkcell and Cosmote as the mobile network operators, and Ericsson will be the vendor for both operators. And then we have Wings and IMEC here as 5G onboard unit providers, and roadside units are provided by IMEC from Belgium again. And for application development, we have ICCS from Greece, Wings again, Ford and Turkcell, and IMEC is also going to be doing some part of it. And then Wings has a cloud application, and TÜBİTAK Bilgem from Turkey will be developing a cloud application again. And we also have the Finnish partners Aalto as doing an important task in our corridor. So in numbers, looking at, we have 5 node Bs, and we're going to be using the NSA architecture. So we have 2 trucks from Fort Otosan, 3 onboard units, 2 onboard units from IMEC and 1 onboard unit from Wings. And for roadside unit and edge app and cloud app, we have 3 roadside units, 3 edge applications, and 2 cloud applications. And user stories, we have 4 user stories. And I'm going to explain next what we mean by user stories. And as you can see, the queue can be quite dramatic at certain times, and especially in high seasons in summer where people are doing their vacation, traveling from Turkey to Greece, or other people traveling. So we have 4 user stories, and we divide these user stories into 2 categories based on the 3GPP use case categories. Platooning is one of them, and extended sensor is the other one. For platooning, we have platooning and see what I see. And for extended sensors, we have truck routing and assisted border processing. I mean, these are actually user stories. We call them, and we named them after the use case category that's the most dominant, but they have a flavor from different use case categories as well. So let's talk a little bit more about this. I mean, in terms of stories, we will look at them as stories. So the idea with trucks travel long distances, and they carry cargo, and the drivers, because they travel long distances, as you see, for instance, here, it is meant, and the roads are known. So this platooning concept has evolved from that. One of the drivers, the leading one, drives, and the rest of the trucks just follow them automatically, and at distances which is much closer than what the human driver can do. And this creates a windshield and eliminates excessive gas usage, excessive fuel usage. And that's the idea of platooning. So there will be a truck driver, and he wants to join a platoon, and he's looking for one, and he wants to join it. And if he's accepted, then we're going to be looking into next the automatic driving functionality of the platoon. We will be looking into joining the platoon, maintaining the operations on the platoon, and then dissolving the platoon, leaving the platoon when it's necessary, because you cannot continue at some point. Those are going to be tested in our scenario, which we call the story. And next, we also talk about the see what I see functionality, because when you're following a very big vehicle in front of you, this is what you actually see, this right the back of the other vehicle, which is very big. And with this, we want to transmit over the 5G network a video stream from the leading vehicle to the ones that are following at the back, so that they can see actually what he's saying on the road in front of them. So this eliminates anxiety, and it provides some kind of, it gives them the option to be able to leave the road and go on their way when it's required from them. So, I mean, let me remind again, I mean, in this project, we're focusing on 5G and network communications in particular, and we try to look into those user stories that are more dependent on 5G and network connectivity. And overall, I mean, this is what happens. Platooning messages and the video stream is sent from the leading truck to the follower trucks. And that's the idea of the platooning use case category. And once we reach the custom side, because we cannot go on forever and without stopping from one side of the border to the other, we have to stop at some point. And then the platoon has to be dissolved. And on the Turkish side, there's an X-ray building, and there are X-ray checks if that's requested by the authorities. So in order to save time, we have developed a user story where the driver will be leaving the truck at some point, and then the truck will be moving autonomously to the X-ray building to perform X-ray checks. And in the meanwhile, the driver will have the ability to do some paperwork on his own. So that this will save time, and the idea is to transfer platoon members from one side of the border to the other as fast as possible, because this area is crowded and there are pedestrians, and it's good to have the transport from one side to the other as fast as possible. So that's the idea of this user story. As you've seen, they are developed based on actual needs and the conditions of the GRTR cross-border corridor. And this is actually the story. I mean, there's a X-ray inspection that is going to be made. I mean, if you look at the third picture, and then the driver gets off, and then this is actually where we will be performing some kind of logic to move the truck autonomously from the area where it's dropped to the X-ray building. And if after the exit inspection there are nothing being smuggled or anything, everything's fine, and then the truck will be on its way to the other side of the customs zone. And I mean, this is kind of the performance we expect to see, moving autonomously, thanks to these roadside units all along. And looking at a higher level picture of what's going on, this Tubitak will be building a cloud application, and it's going to be collecting LiDAR images from the roadside units and also from the truck. And based on that, it's going to be calculating the path to be followed by the truck to the X-ray building. It will collect all information. And for that, the cloud application will be using a local dynamic map. It's in 4 layers, moving from the static layer to a very high dynamic layer. And it will have a path planning node as well for sending the safe waypoints to the truck itself. So that's kind of the idea. And our last user story here is developed by WINS, and it is the idea of, so if we put on a lot of sensors and the necessary technology on the truck itself, on the vehicle itself, why does it have to be stopped and checked? The idea is to have a non-stopping behavior for the vehicles from one side of the border. So they will have carbon dioxide sensors, for instance, or other cargo checking sensors. And it will be checked against the truck manifest itself. So if there are no, for instance, human, livestock, or cattle, I mean, that kind of smuggling things, and or unauthorized cargo, the truck will be, or the vehicle will be issued low risk, and a zero-touch border crossing will be allowed, for instance. And we will also check for the movements of the customs agents, personnel on the field, and they will have to be ordered autonomously, or ordered to be stopped by the application if there's a trajectory that's passing through the path of the vehicle itself. So that's kind of the idea, and this is why we call them user stories and not use case categories, because there's a story behind all of these activities. And these are some of the user interfaces developed for the assisted border crossing. And I mean, this is what we have, equipping the vehicle with sensors and putting a plate recognition system and an automatic border gate that will order, it will be closed if there is something suspicious on the vehicle. And then we will have camera pictures, light status, truck manifest document from the authorities, carbon dioxide, NFC, LiDAR, and GPS information from the field. And then they will have instruction messages transmitted from the application itself. So coming to the 5G network parts, so this is our architecture. As I've said before, we're working with Ericsson and on both sides. And at the time of deployment, we decided to go with NSA option 3X. And since this is NSA, we use LT for anchor. It's 2,600 megahertz band as anchor. And for the NR, we use 2 different bands. And the sites we have at the cross-border region, we have 3 sites on the Turkish side and 1 site at Kipi. And we also have an additional site at İnönü. İnönü is the Fort Ultrasound plant long-term development testing area we have. And the transport networks are going to be have to be connected. So, I mean, in pictures, we start with a network design, what to deploy which architecture and where to put the equipment, which sites. And do we have to do any transport network upgrades in these areas? So these are things we looked into. Radio access network deployment integration completed, as well as core network. We started with end-to-end network testing as much as we could, and IP network implementation, interoperating testing is what we're looking into now. End-to-end network testing is done for core and radio on both sides. And these are some of the pictures we have from both sides. Sorry, just I have a small problem. Okay. So these are the interfaces we have. The network interfaces. It's a very detailed overview of the interfaces that need to be thought about for the trial. These two networks, cores, they're both, we call them overlay as test networks. They're not part of the live network, because when we started the project, both Turkcell and Cosmote were using test frequencies. We didn't have commercial 5G services in both countries. And now Cosmote, Greece has 5G commercial operation, but in Turkey we're still pending the auction. So we're using the test frequencies we get from our regulatory bodies. And let me continue. I mean, we deploy, this is an NSI architecture, is an S gateway, MME, P gateway, and the other equipment, and the edge applications are here, and cloud applications. So I'm going to show this slide for roaming. I mean, this has been the topic of discussion in the morning sessions. And I mean, home-routed roaming is actually the key with the NSA architecture for obtaining service continuity while doing handover from interparliament handover from one operator to another. And this is kind of what happens with when you roam from handover, let's say handover from Turkey to Greece, and you camp on this G node B. All traffic is coming from the S gateway on the Greek side over the connectivity or the transport connectivity between the two operators to the P gateway. If you want to have IP connectivity, then you should ensure that the connectivity is not lost. And for this, you have to define the G node B on the Greek side as a neighbor of the base station in Turkey. So its ANR function should be working here if you want to do an active transfer. And normally, operators have S6A and S8 interfaces between them, but not the S10 interface, which would transfer the context information to continue the session. And in our setup, we also have the S10 interface. And so this will allow a service continuity for our case. And local breakout, I mean, with home routed, you may guess why there's a long latency, because the traffic is coming from the Greek side to the Turkish side, the P gateway, and in between. This connection between the two operators, it can be over GRX or with the GRX, for instance. This is Turkey and Greece, but the GRX operator can be anywhere in Germany, for instance. Then in this case, the signal will be traveling from Turkey to Germany and back to Greece, and this creates long latencies. Our idea is to make a direct connection so that we can confine the latency as much as we can. If we want to do local breakout causes service discontinuity, because You get a new IP from here on the Greek side, and this is a cause of service discontinuity. In this case, there will be a disruption, but the latency will be considerably less because you will not be going back to Turkey, obviously. And these are what we're going to be trying to see what the performance is actually on the field. So, I mean, our observation is that the inter-parliament handover will be in between the two borders. So right here on the river. So this is inter-parliament handover, and we have a guess as to which user stories we can test with inter-parliament handover and which can only be used for roaming. So these are some of the issues we're looking into. We've done some tests, and it is coming a little slower. Okay, the Turkcell, this is the Eskişehir, the Hordozasan plant. We talked about the NR site is here and factory test area is here. This area we're going to be using for long-term development and testing. And looking into that area, we did, for instance, this downlink TCP stationary test. We see 712 peak rates. And these are sufficient considering that we have a backbone of 900 megabits per second, which also carries a lot of traffic. So this is good for testing our scenarios. And these are some of the other results. This is the uplink cell capacity. Uplink is important because when you talk about this truck routing or other scenarios where you will also be sending video streams or images from the field, uplink becomes important. With more UEs, the rate drops, obviously. And this is something we observed. And we also looked at the downlink throughput during mobility with UDP. And on average, UDP is 418 megabits per second throughput. And this is a border area. I mean, pictures of the antennas and the tests. I mean, as you can see, there are figures of 843 IC, 900 something. These are thick rates for downlink and uplink and 5G. So there are some of the results we obtained. So, okay. Yeah, I think I have 4 or 5 seconds delay between my transition and what you see. And mobility test results for download, we looked into those. And for download, these are kind of, let's look at the peak download and average. Peak, we saw 862 and 716 on the QP side for peak download. Again, here, the transmission backbone is important. It's not just core network or RAN we should look into, but what connects the equipment is also important on transmission links. And although we're saying we have an overlay and test network, please bear in mind that the transmission network also carries live traffic. So it's not just a pure overlay in that sense. And for uplink, we saw peak rates of 159 in Uppsala. On the Turkish side, on the Greek side, we saw 65, but we're using uplink carrier aggregation on the Turkish side, and the other side was not. So that's one of the reasons for this behavior. And in terms of latency, it's 12 milliseconds minimum on average, 21 milliseconds on both sides. This is a graphic of the Uppsala region for latency. And mobility tests, we wish to do mobility tests and handover tests crossing from Turkey to Greece and Greece to Turkey in both ways. But at the moment, the border area is closed. And physical crossing of the border is not possible because of COVID-19 restrictions and other problems we had. So what we did while we're waiting for the borders to be opened, we did a pore-to-pore connectivity testing using ICMP ping messages. So we use these 4 components to test because, as I said, we're going to have a 6A interface, an S8 interface between the 2 pore networks. So we tested all interfaces, and we have a check for almost all interfaces for now. And we will continue with physical cross-border testing when the border is reopened. So a little bit more on the equipment. It's not just important what you have on the network side, but your equipment is also important. For instance, for Wings onboard unit, the network speed, they have 1.2 gigabits per second, but the hardware caps at 400 megabits per second. So they have a 370 megabits per second with this equipment. So this is good. I mean, the equipment is also important. And for IMEC, onboard unit, roadside unit, they don't have 5G facilities for testing. We did the testing at Turksal Plaza. And there we have a similar situation. So they have a 2x2 MIMO. And therefore, we achieved 587 megabits per second and around 85 megabits per second uplink during our tests. I mean, the equipment is important as well, but let's take a note of that. And for the ultrasound truck, because we talked more about 5G today, as I mentioned before, it's 5G for CAM. So, but the Ford ultrasound truck is a very important component of our trials. And I mean, this is the inside of the truck. So what makes it autonomous? They put in a micro box component in it for decision making, and it controls the electronic control units of the vehicle. So these all have to be fine-tuned and have to be working together. And CV2X is feeding into the decision making here, as well as the sensors and the HMI. And they have done a lot of work to complete all these activities. So this is inside the truck itself. So they put in the equipment down there, micro box you see here, and they will also have the onboard unit inside here. This is like the bed part of the vehicle. And the team, very good work, thank you. And for integration, what are we doing? So for onboard unit 5G integration testing, we did, and the RSU testing we did, and the integration of hardware, software, those are all complete. And the onboard unit and vehicle integration are done, as well as the integration of the 2 onboard units and the vehicle. Now we're working on integration between the applications and the rest of the components here, 5G and the truck and the onboard units. And we wish, as the next step, we wish to start trialing in June. So that's kind of our plan for the rest of the year. And if everything goes fine with COVID, then we can do more work at the cross-border areas and make some more progress on that part as well. So that concludes my presentation. Thank you very much for listening. Let me look into the chat box as well.
Yeah. Thank you, Nazli. Thanks for this comprehensive presentation. I have a number of questions. Let me start with the last one. The first thing is, given that we are talking about a hard border, the issue of delay is always relative. If you have to stop anyway, the issue of delays that you mentioned are maybe not that important, because you can use the time you are stopped there to prepare the network. Is this feasible? Can you prepare, knowing the trajectory of the trucks, can you prepare the network so that you reduce or get rid of any interruptions? Can you do that?
Yes, well, I was playing around with the application, so I couldn't quite get the question. So
since you have to stop anyway because of the hard border, can you use this time to prepare the network so that you preemptively establish the connectivity and therefore reduce the delay, if possible, to zero? Can you do that? Is it feasible?
yeah, the delay is actually caused. I mean, we should look into the reasons for the delay. I mean, what happens is with commercial networks is that the two networks do not share information about, for instance, neighbor information. What the two operators want, commercial network operators want, is the connection to drop, and then you start with a new operator. I mean, this is what all commercial operators do. And there's no, for instance, this interface I showed you, this SN interface, it's not established. Why not? Because both on the core network and on the radio access network, you have to do some configurations. And if you, I mean, in our setup, we have just Turkcell and Cosmote and two operators. But if you think about, for instance, in Turkey, we have 3 operators. And on the Greek side, you might have another 3 operators. And in Bulgaria, you also have maybe 3 operators. All these operators, they will have to share information about neighborhood information. And if you have more than 1 operator, and then which operator will you switch to? This needs a lot of pre-planning, which is not just doing it while the vehicle is moving just for this vehicle, but for in a general setup, you have to do this. And this setup, we don't have it because, I mean, also a lot of configurations are needed, and also for charging reasons, the operators do not wish to have this interface. If they want the service to stop and then restart from the other operators to see that there's a transition. So, I mean, it's not just technical. The standards are there. This S10 interface is defined, but commercial operators do not use it, and that's one of the reasons. So, yeah. I mean, yeah, we also thought about it. For instance, when to start local breakout, we thought the vehicles, they will have to stop somewhere, and then from home routed roaming, we can switch to local breakout when they stop. For instance, we can trigger that. That's that kind of configurations we thought about as, I mean, that could be offered. But other than that, it's not just getting the prepared, is something that should be a more broad activity of configurations.
Yeah. So another question has to do with go a little bit above connectivity. So are you depending on application reconnection, especially from the cloud applications? Are you depending on an application reconnection, or can you somehow enforce an interrupted service? How could you do this? If it's only the application that has to reconnect, you are talking about UDP stuff, so the application has to be aware of this. How do you enforce an interrupted service?
Yeah, for home routed scenario, for instance, with roaming, the IP connectivity is still in the home operator. I mean, the first operator, let's say. So the application can stay there, connected to the P gateway. And for this scenario, we don't change the application instances from one side to the other. With local breakout, when you switch the P gateway to the visited operator, for instance, Greece, if you're traveling from Turkey to Greece, then you will have to switch to that instance of the application naturally, because otherwise you will have to travel to Turkey back for getting application information, which is nonsense. So you should have 2 instances. I mean, depending on the application design, you might want to exchange information among the 2 applications. And with local breakout triggered, you save time there because there's a service disruption. And then in the meanwhile, we can change information, exchange information between the 2 instances of the application if you wish. For what we will be trialing for platooning, for instance, I mean, looking into the geography and I mean the cross-border area. And since we cannot keep on doing platooning in the customs zone, they will anyway be in the under the coverage of Cosmote when they go to Greece. So we cannot do this for platooning, but for the other applications, we can try to test these.
Okay. Very good. Thanks again. So thanks for this compound presentation of the project 5G MOBIX. I would like to thank the 3 projects from the first call on 5G for CAM. And we will, as soon as my agenda comes up,